Okay, we say that energy is the capacity to do work. Then the units are joules. You need it to be in capital J, otherwise you'll be marked wrong. What else do we say? Energy is a scalar, so it does not have direction, okay, unlike your vectors. We concluded that Captain America, he had more energy because he can do more work. So we have seen this example. Wind is being used to turn turbines that convert kinetic energy to electrical energy. Okay? Moving objects, they have kinetic energy and it can be used to do work. So this is one example. So in the past, the people used battering ram. There's kinetic energy that is used to break down the walls and gates of ancient castles. So now I want you to compare between this table tennis ball and a bowling ball. Which one has more kinetic energy? So over here, we have a table tennis ball. Some information for you, it weighs 3 grams. Shufi, what's happening? Is there something wrong? Table tennis has a mass of 3 grams and a bowling ball that has a mass of 6 kilograms. They are both starting at the same point, okay? Right now, do they have kinetic energy? Why? And because they're not moving. Okay, so now watch how they move. Are they moving at the same speed? Yes, they're moving at the same speed. So one more time. Okay, based on this and based on your instincts, which one has more kinetic energy? Why do you say so? You know instinctively that it can be used to do more work, right? Consider the earlier example, the battering ram. You think the bowling ball can knock down the door or the ping pong ball can knock down the wall? Because it has to be the bowling ball. So what is the difference between these two? The mass. The mass contributes to the kinetic energy. In other words, mass is a factor for kinetic energy. So when I want to calculate kinetic energy of an object, I must consider its mass. Okay? Whoops. So, kinetic energy depending on the mass, the greater the mass, the greater the kinetic energy. Okay? So now, I have 2 bowling balls. Which one has more kinetic energy? They have the same mass this time, Okay, so one more time. Watch the difference. Okay, which one has more kinetic energy? Why do you say so? It is moving faster. It has a greater speed. So instinctively again, you know that you rather get hit by the red ball than the blue ball, right? Because the red ball, moving slower, has less energy compared to the blue ball, which is moving faster. So what can you conclude here about kinetic energy? It also depends on the speed of an object. So far we know that kinetic energy depends on mass. Now we know that it depends on speed as well. The greater the speed, the greater the kinetic energy. Okay? So the kinetic energy is given by K equals to half mv squared. Have you all seen this before? Okay. So we have a constant here, and then we have mass. And what does V stand for? Velocity or speed. So can you see from this equation, mathematically speaking, if m increases, that means the mass gets greater, what happens to the kinetic energy? Increase also. The greater the mass, the greater the kinetic energy. This is seen mathematically. It gels with what we observe in reality. When I ask you about the ping pong ball and the bowling ball, they're different mass, same speed. We know that bowling ball has greater kinetic energy because of the mass. Okay, so likewise, as your speed increases, your kinetic energy also increases. Okay? So you need to memorize this. Mass must be in kilograms. The speed will be in meters per second. These are SI units, and your kinetic energy will be therefore in joules. Okay? So an example. You've seen this before already. You can jot it down in your textbook if you want to. But otherwise, I think it's really easy. 50-gram toy car. This is the mass. Moving at constant speed, 2 meters per second. Determine kinetic energy. What should we write first? Did you just write half mv squared? You must write equations. I don't like to see just half mv squared. Then what? What is that supposed to be? You must write down an equation. Something equals to something. Okay? So from here, we substitute in half, which is 0.5, m, which is 0.05. Because of 50 grams, we need to convert to kilograms. And 2, which is the speed. So you get 0.1 joules. Okay? Straightforward, basic. Next, potential energy is the stored energy in a system. Then it has a potential to do work. Okay? So we have chemical potential energy found in food, fossil fuels, and batteries. You have your elastic potential energy in your rubber band, in a bow and arrow. And gravitational potential energy over here, I think this is a power driver. So it raises this driver up, then it releases it, and it slams down into the floor, and it does work. Okay? So you raise it up, and then it has gravitational potential energy. So today we are going to focus on gravitational potential energy. We consider table tennis ball and bowling ball again. And we want to think about which one has more gravitational potential energy. Whether it's the table tennis ball mass 3 grams or the bowling ball with a mass of 6 kilograms. They are the same height above the ground. Okay? Same height. So which do you think has a greater gravitational potential energy? Meaning it has a greater capacity to do what? Bowling ball. So let's say you want to smash something on the floor. The bowling ball will be able to do a better job. Okay? And that is by virtue of its... What is the difference between these two that causes it to do more work? Mass. So we conclude that gravitational potential energy must depend on the mass of an object. The greater the mass, greater the gravitational potential energy. Okay? Next. Red bowling ball, blue bowling ball, different height from the ground. Which one has greater capacity to do work? Red ball. And why is that so? It has a greater height from the ground. So height of red ball greater than height of blue bowling ball. So the greater the height, the greater the gravitational potential energy. And now we can write down our equation for gravitational potential energy. It is called mgh. Guess what is m stand for? Mass. So the greater the mass, greater the gravitational potential energy. What does h stand for? Height. Greater the height, greater the gravitational potential energy. What about this g over here? Okay, is your gravitational field strength or your acceleration due to gravity? How much is the value? 10. Okay, so your answer will also be in joules. In this case, they use G, gravitational field strength, newtons per kilogram. Okay? What does this mg remind you of? What does this mg remind you of? Weight. Right? Weight is equals to mg. Okay? So what you need to know is just GPE equals to mgh. Just know at the back of your mind, if they give you the mass of an object, you need to multiply by 10, then you multiply it by the height. And at the same time, when you multiply by 10, you are actually calculating the weight. Okay? So, example, 5 kilogram box, raised 50 meters. What is the gain in gravitational potential energy? So I need to state, I need to tell you that the gravitational field strength is 10 newtons per kilogram. What happens if I don't? If I don't tell you this, then maybe it is not happening on Earth. Maybe it's happening on the moon. Then your gravitational field strength will be different. Therefore, your gravitational potential energy will also be different. Okay, so in this case, I tell you that it is on Earth by telling you it's 10 newtons per kilogram. So solution, write down your formula. Don't just write mgh. This one doesn't really give you any marks. However, the correct substitution in the next step gives you marks. Show me. You know what is m, what is g, what is h, and then you get the final answer. Okay? Any questions so far? Now a ball is tied to a string and allowed to swing freely. How can we get the ball to start swinging? How? Okay, let's pretend that this is a ball, okay? It is tied to a string and it's allowed to swing freely. How can we get this to start swinging? Push, right? I need to push it, right? When I push it to a side, what happens to its position of CG? Okay, so initially it was over here. So the CG probably somewhere in the middle. When I push it to the side, what happens to the CG? Did it get higher or did it get lower? Get higher, right? So if the CG get higher, what can you tell me about the gravitational potential energy? Higher. It has a higher gravitational potential energy when I move it to the side. Okay? Where did this energy come from? From me. I supplied the energy to push it to the side. Okay? So now it has higher gravitational potential energy as compared to the earlier position. Okay, what happens if I release? It's going to swing. Swing and swing and swing, right? So why does that happen? So let's see why that is so. Then we will try to answer this question also. When does it have the greatest gravitational potential energy? When does it have the least gravitational potential energy? When is the kinetic energy greatest and when is this lowest? Okay? So I shall move on to the next portion on energy, the principle of conservation of energy. This one is very important. Open to your textbook, find this, highlight it, put stars around it. Which page is it on? 107. Page 107. At the top, highlight it. This is a principle. It does not change. Conservation. That means the total amount, whatever it is, we preserve it. Okay? The principle of conservation of energy tells us that energy cannot be created, it cannot be destroyed. It can only be converted from one form to another. And the total energy in an isolated system is constant. So this is the full definition. High chance it will come out for our exams. We like to test this. Okay, so please memorize it. Anybody doesn't understand? Okay, you cannot create energy, you cannot destroy it. Huh? So right now we have a pendulum, string, bob, the three different positions. Original position is at B, where the CG is directly below the pivot. I move it to the side. Okay? Then I release it. State the energy gained by the pendulum at A, B, and C. Okay, so right now when I move it to A, it gains gravitational potential energy because the CG is raised. So when it comes down to B, there is movement, right? So there is a gain in kinetic energy. Earlier on at A, I'm holding it. Does it have kinetic energy? No kinetic energy. When I release it, it starts to move. At point B, there is kinetic energy. When it goes to point C, what happens? Any more kinetic energy? No more kinetic energy because you'll stop for a moment over there. And then it gains your kinetic energy again. Okay? So this is the GIF. Show you what happened. So it swings from the extreme ends, from A down to the lowest point B, up to the highest point again C, then B, then A. Okay? These dotted lines tell you where the lowest point of the pendulum is. And we see that between A and B, there is a gain in the height. That is h. From B to C, there is a gain. From A to B, there's a drop in height. From B to C, there's a gain in height. Okay? And these two heights, they are the same. Assuming, what assumptions are we making here? No what? No air resistance, what else? Because if there's air resistance, it will slow down, right? So what other reasons, what other assumptions are we making here? Nope, not that. Friction. The pendulum is swinging at a pivot, right? So at a pivot, you have a string, so there is movement. So friction will cause the total energy in the system to be reduced. So over here we assume no friction, no air resistance, therefore it will just keep swinging forever and ever. Okay? So earlier on in this example, I show you, I started plotting out from the bottom of the board to this blue line to this point. So now over here, I use the CG. From the CG, look at the position of the CG. There is also a gain, right? This gain in height is the same as what was in the previous slide. Okay, it's the same thing. Just that I use my reference point as the CG over here. Earlier on, I used the reference point as the bottom of the pendulum. Okay? Now, the ideal pendulum. We say it's ideal because we are assuming no losses due to friction or air resistance. When I shift it to the side from the original position, so now it's at point A, and the height is h centimeters above the original position. It gains gravitational potential energy because you raise it up, and that will be mgh. Okay? So now, when I release it, it goes down to B, and then I pause over here. Of course, we expect it to continue, but I pause here. Let's discuss what happens over here. When it's released from A, it swings towards the equilibrium position, which is at B, and the gravitational potential energy earlier on, it is converted to kinetic energy. Why do we say it is converted? Because earlier on, your gravitational potential energy at A, right? At point B, the gravitational potential energy is reduced because it is at a lower height. Where did the gravitational potential energy go to? It must go somewhere. It cannot be destroyed. So it is transformed to your kinetic energy. That is why there is movement. So at point B, the GPE is minimum while the kinetic energy is maximum. During our exams, you are not allowed to write GPE, La, KE, all these kind of things. Okay? Spell it out in full. Then, let us resume the simulation. When it goes back to B, it is going to continue to rise up again. And then it will pause for a while at this position C. That is the other extreme end. So it gains gravitational potential energy, but it loses kinetic energy. How do we see that? Gales, how do you think we can see that it loses kinetic energy? Yeah, it loses kinetic energy. Yeah, because it stops for a moment. When you swing it to the other end, okay, this is not very nice. A longer pendulum, you'll be able to see better, okay? Goes to one end, pause for a while, swing to the other end, pause for a while, swing to the other end. That pause over there shows you that kinetic energy is now zero. So where did the kinetic energy go? It went into your gravitational potential energy. So if it is ideal, the bob will swing all the way up to point C, which is the same height as when it was released. Meaning it will continue forever and ever. So this is because of conservation of energy. Energy cannot be created, it cannot be destroyed, but it can be converted from one form to another. So instead of pendulum bobs, we can also use bouncing balls as an example. You all play sports during your PE. Probably played basketball before. Okay? When you drop a ball from this height, bounce, goes back up. Does it ever go back to the same height? No, it doesn't. Why is that so? Because there are losses in energy. Okay? When you drop the ball, you hit the floor, right? What do you hear? Sound. Is that energy? Where did it come from? From the ball, with contact with the ground. Where did all this energy come from? All from your gravitational potential energy to begin with. as it travels through the air, there is a bit of air resistance also, right? When it hits the floor, there is some friction also, right? All these are all your losses in energy. So that's why it doesn't go back to the same height. So in this case, if we say that it is an ideal situation, no losses, it will go back to the same height. Okay, so right from the start, there is gravitational potential energy. If I just drop it, at the moment when I drop, it has no speed. No speed means no kinetic energy. So when I release it, all the gravitational potential energy is converted to kinetic energy. So your gravitational potential energy decreases because the height above the ground gets smaller and smaller. So GPE naturally will become smaller, right? And then kinetic energy will increase. Okay? When we say kinetic energy increases, can you remember what is the formula for kinetic energy? Half mv square, right? And then I say kinetic energy increases because GPE decreases. Make sense or not? Or your GPE, it is decreasing, then it is converted to your KE, right? So it makes sense. Your KE is increasing. But you know that KE is half mv square. Half is a constant. Does the mass of your basketball change? It doesn't change. So what must change? Speed. KE increases, meaning half mv square increases. Since your half cannot change, m cannot change, therefore v must change. So what can you tell me about the speed of the basketball when you release it until it hits the ground? It increases in speed. Okay? Isn't that what we have learned for dropping of stuff? Your loss, F equals to ma. Things that are dropping, they accelerate, right? Due to gravity. They accelerate at a rate of 10 meters per square second. So, as it drops, the speed gets larger and larger. So you see these two topics, we have now different ways of explaining why the speed of an object that is dropped increases. Okay? No contradiction. Different ways of explaining it. So just before hitting the ground, kinetic energy is maximum. Just before it hits the ground. And then your gravitational potential energy is the lowest. Upon striking the ground, the kinetic energy is converted to elastic potential energy. Go and Google, go and find YouTube of tennis ball or any balls that are bouncing in slow motion. Okay, you will see that the ball will be deformed. It will look like it's being squashed when it strikes the ground. Then after that, it regains its shape and then it bounces out. Okay, go and find the video online yourself. And then at maximum height, the kinetic energy is 0, the ball is not moving, gravitational potential energy is maximum. It is going to be at the same height. Okay? So, because of conservation of energy, when we assume no other losses, then it will be at the same height as which it was dropped. Any questions so far? Very familiar to you? Okay, good. So example, ball 500 grams is dropped from a height 10 meters. What is the initial gravitational potential energy? What should we use? Children here. What should we use? What did I say about you guys writing MGH only? You must write GPE equals to MGH. Then check that everything is in SI units. Is this SI unit? No. So change it to half kilogram. Okay? So GPE equals to MGH. M, half kilograms. G is 10 newtons per kilogram on Earth. And the height 10 meters, so 50 joules. Determine its velocity just before it hits the ground. How should we do this? Okay, think about it. How do we determine the velocity? Okay, KE. Okay, KE equals to half mv square. By principle of conservation of energy, the initial GPE is converted into final KE. So we are saying that kinetic energy is half mv square. All of this energy came from your gravitational potential energy. Because that is the only energy it had when it was at the top. So 50 is equals to half mv squared. Then solve for v lah. Okay? So this is how we write an equation based on this principle. Alright? Okay. No time. You all seen the video of the guy holding a bowling ball at his face, then you release it? Saw it before? Okay, next lesson I show you all, okay? We only have about 1 minute plus, so let me talk about your homework. Workbook, worksheet 6A. Yeah, 6A.